The purpose of this video presentation is to create a C++ program that will approximate the root of a given transcendental or polynomial equation using the SECANT method technique. But before we build the C++ program, we will briefly discuss the basic principle, the formula, and the algorithm behind this type of approximation method. Let's discuss briefly the second method from Figure 1 graphical representation. For example, this is our curve f of x with the root r lies along the x-axis. The secant method is a root finding algorithm that uses a succession of roots of secant lines to better approximate the root of a function. The secant method can be thought as a finite difference approximation of Newton's method. However, the method was developed independently of Newton's method and predates back by over 3,000 years. We have here the x sub 0 and x sub 1 for the first secant line. At n is equal to 2, we can compute the value of x sub 2, the intercept of x with this secant line. X sub 2 is equal to the x sub 1 minus the function of x sub 1 times x sub 1 minus x sub 0 divided by f, the function of x sub 1 minus f, function of x sub 0. For the second iteration, the x sub 1 of the first iteration became the x sub 0 of the second iteration. And the x sub 2 of the first iteration became the x sub 1 of the second iteration. And we will get another approximated root x sub 2. This process is repeatedly performed until x2 is close enough to the actual root. Okay, so as we can see from here, the x sub 1 of the first line, the red one, became the x sub 0 of the second line. Okay, and we have the new approximated value closer to the actual r. The second method is defined by the recurrence relation, which is this equation x sub n is equal to x sub n minus 1 minus f function of x sub n minus 1 times x sub n minus 1 minus x sub n minus 2 divided by the difference of the function of x sub n minus 1 minus the function of x sub n minus 2, whereas the n must be greater or equal to 2, minimum of 2. At n is equal to 2, we'll substitute the value of n in this equation. We will arrive at this new equation, x sub 2 is equal to x sub 1 minus f, as f function of x sub 1 times x sub 1 minus x sub 0 divided by the difference of the function of x sub 1 and x sub 0, which was discussed previously. At n is equal to 3, we will substitute 3 in this equation and we will arrive at this new equation. The x sub 2 of the previous equation will be transferred here and the x sub 1 will also be transferred here. Repeated iteration is being performed until the absolute error or the accuracy E is achieved. The iteration is terminated when the absolute value of the difference of x sub n minus xn minus 1 is less than or equal to the required E. This x sub n is the new value minus the previous value. Then x sub n will be the approximated root, which means that x sub n is close enough to the actual root. So, as can be seen from the recurrence relation, the second method requires two initial values, x sub 0 and x sub 1, which should ideally be chosen to lie close to the root. Okay. The purpose of the C++ program is to solve a root x2 of a given function using the secant method. Let's discuss the algorithm and the flowchart simultaneously. We will start by entering the initial values x0 and x1, enter the precision p and the accuracy e, and we will begin the loop. Okay, so for x2 is equal to x sub 1 minus function, the f function of x sub 1 times the value of the initial x sub 1 minus x sub 0 divided by the difference of the function of x sub 1 minus the function of x sub 0. Then for the next iteration, we will set the x sub 0 to the x sub 1 here. Okay, and then we will set the x sub 1 for the next iteration for this value, and then until the absolute value of x2 minus x1 is less than or equal to the accuracy. If the answer is no, then we will repeat the process. Okay, repeat the iteration until the absolute value of the new value minus the old value is less than or equal to the accuracy. If it's yes, then we will print the root, and that will end our algorithm. Now, there are two parts of the C++ program. Number one is to solve the root of transcendental equation, and number two is to solve the root of a polynomial equation. So let's take a look at the C++ program for transcendental equation. Let's go to the code block. We will use the code block as our compiler. First thing to do is to write the simple description of our program, C++ program for secant method. And we will just hide this with 2 slash. And then we start by writing the library headers. Okay. Number one here is the IO stream. IO stream headers defines standard input and output streams, which includes console in, cin, or console out. Including this header may automatically include other headers such as IOS, iStream, and OStream. The IO manip, this is the parametric manipulator that includes set width and set precision. The CMath declares a set of functions to compute common mathematical operations and transformations like trigonometric, exponential, and logarithmic functions. The conyo.h is a header file used mostly by MS-DOS compilers to provide console input and output, which includes clear screen, getch, and return. The standard input-output.h, this library uses what are called streams to operate with physical devices such as keyboards, printers, terminals, or with other type of files supported by the system. The standard library.h is the standard general utilities library, includes environment functions like abort, exit, and integer arithmetics. Now, this using namespace standard means make all the things available under the standard namespace. This is the declaration of the variables which are used in the program. Here, we declare double x sub 0, x sub 1, x sub 2, the accuracy E, and the precision P. We declare iter, initialized to 1. The iteration will start at 1 and end the number of segment as the number of segments as integer. The double F parameter is a pointer function, and the pointed function takes a double input and returns a double, which means that this function will be called when being used inside our program. This int main open and close parentheses is necessary for every program. From this line onward, the program body starts. Okay, then let's begin the program. Then let's print out, cout, the title of the program, which is secant method calculator, and then print out also this program obtains the root of this equation. Specifically for this equation, transcendental equation, we have one hidden example here, a polynomial, and the title of this is also hidden with these 2 slashes, which we will be used later. And then we will also print out, enter the 2 initial values, x sub 0, x sub 1, enter initial values of x sub 0, which will be saved in x sub 1, okay, and then x sub 1 will be saved in x sub 2, which means that the x sub 0 of the following iteration will will have the value of x sub 1, and the x sub 1 of the next iteration will have the value of the previous approximated root x2. Then we will enter the precision p, which will be saved inside the p, and then enter the required accuracy e, which will be saved in e. And then we will set the fix for the precision. Okay? Whatever the inputted p will be fixed at that. If it's 6, then it will be fixed 6 decimal places throughout the program. And then we will print also the tabulated results, and we will print cout the description of our table, which composed of iteration x sub 0, x1, x2, the function of x0, function of x1, then a function of x2, and the accuracy. Now let's do the loop. Let's equate x sub 0 is equal to x sub 1, x sub 1 is equal to x sub 2, and then we will perform x2 is equal to x1 minus x1 minus x sub 0 divided by the function of x sub 1 minus f function of x sub 0 times the f x1. Okay, and then we will print the values of the iteration, first iteration, and then the x sub 0, and then x sub 1, and then x sub 2, their functions x sub 0, x sub 1, and x sub 2, and the absolute value, the function absolute value of x sub 2 minus x sub 1, which is the accuracy. If the f function of x sub 2 is equal to 0, 0, then we will print the root of the equation is that x sub 2. And then let's designate n is equal to the iteration. We will repeat the process while the absolute value of x sub 2 minus x sub 1 is greater than e. If it is less than e, then we will that will be the root is the x2. Then we will print this line. This line is the line below the table. This line is below the description of the table. And then we will print therefore after the n iterations, the root is x2 is then the x2, the last x2 here. And get ch. This get ch will hold the terminal or the console. It will hold it until we press any key. Let's try one example, which is this double A. Let's try this example. Okay, let's build and run this program. Okay, now this program obtains the root of f function of x is equal to 1 over square root of 1 minus x raised to 2 plus 4 times 0.1221 raised to 2 times x squared minus 2. So we will input the initial values of 0. We'll input x sub 1 is equal to 1, and the precision set to 6, and then the accuracy we will set it to 0.001. We have the result. We have this. We have here the iteration from 1 to 8, the x sub 0, x sub 1, the values of x sub 2, the function f x0, f x1, and f x2, and also we have the accuracy. At iteration 7, the accuracy is 0.001. Again, performing the iteration at 8, then we have 0.00025, which is less than the required accuracy. Therefore, after 8 iteration, the root x2 is equal to 0.729970. Now let's take another example from our program. Okay, let's hide this equation first, and let's highlight the next equation, which is a polynomial. This equation is a transcendental. This is a polynomial, which is x cubed minus 4x, okay, minus 4x squared plus x minus 10. So we will hide this one and activate this one. Let's build and run this equation. Okay, now it's prompting us to enter the initial value. Okay, and then that is the initial value of x sub 0 is 0 and x sub 1 is 1, and then we will set the precision to 6, and we will set the accuracy to 0.001, and we will have these tabulated results. So we have the iteration here. We have x sub 0 up to required accuracy. Now, at a 12th iteration, the accuracy is 0.002, which is greater than 0.001. At 13th iteration, we have 0.000001 as the accuracy. So therefore, after a 13th iteration, the root x2 is 4.306913. Now, this is the first program. Let's proceed to the second program, which is for the 3rd to 10th degree polynomials. Okay, let's hide this first program by pressing slash and asterisk, and we will close it. We will close it at the line 64 with asterisk and slash, and we will remove the slash and asterisk for the second program, and we will also remove this part. Okay, and then okay, this is the second program for 3rd to 10th degree polynomials. Second method, okay, this is the description. We include also the IO stream, IO manip, CMath, the conio.h, standard input-output.h, standard library.h. Okay, and using the namespace is also included, and we declare a this is the coefficient of our equation, polynomial equation. They are declared as double: x sub 0, x sub 1, x sub 2, x sub 0n, x sub 1n, function of x sub 0, function of x sub 1, function of x sub 2, function of x sub 0n, function of x sub 1n, the precision and the accuracy. We declare degree, the I, and iteration as the integer. We will start the program by inputting the integer main, open and close parentheses. This is necessary for every program. From this line onward, the program body starts. So we will print cout, the title of the program, second method calculator, with a new line. The cout also, this program obtains a root of 3rd to 10th degree polynomials, end line and semicolon, cout to enter the degree of the function, which will be saved inside the degree. If the entered value is greater than 10, we will print the degree you entered is out of range. Then the program will be terminated. Else, if the degree is less than 3, then we will print in the console the degree you entered at out of range, and the program will be terminated. Else, repeat this loop if for I is equal to degree, and then I is greater or equal to 0, then the I minus minus will decrease it until 0. So A, if you input 5, then and we will print enter coefficient of x raised to I, for example 5, and then A, the coefficient of 5 is equal to, we will repeatedly enter, for example 5, and then decrease by 1, 4, 3, 2, 1. And then we will print enter precision decimal points P, which will be saved to inside P, and then enter the required accuracy E, and then set precision P. The P will be called from here. Okay, for example 6 decimal places, and then this will fix the desired precision throughout the program. The console will print also enter two initial values, x sub 0, x sub 1. Okay, x sub 0 will be saved to x sub 0n, and then enter initial value f x sub 1, then it will be saved to x sub 1n. If x 0n is equal to x1n, then we will print the error, the assumptions entered are equal. Else, we will print the tabulated results, and then print the description of the table, which are iteration x0, x1, x2, the function of x sub 0, function of x sub 1, function of x sub 2, and the accuracy e. Okay, and then the iteration plus plus will increase 1 every iteration. Let's set x0 is equal to x0n, x sub 1 which is equal to x1n, and then perform the f x0 to this equation, okay, up to a sub 0, and the same will be performed for x sub 1. X sub 2 then can be computed by x sub 0, okay, minus f x sub 0 times x1 minus x0 divided by the function f function of x1 minus f function of x2. Then fx2, it will be computed also, the value of x2 will be computed here. And then we will print out the values of the parameters, the values of the variables, the iteration number, the x sub 0, the x sub 1, x sub 2, fx0, fx1, fx2, the absolute value of x2 minus x1. And then we will equate for the second iteration, equate x0n is equal to the x1 here, and then the x1n for the next iteration we will equate is equal to x sub 2. We will perform this loop until the absolute value of x2 minus x1 is greater than e. We will perform this loop while the absolute value of this new value minus the old value is greater than e. And if it is less than, then we have the approximated root. Okay, we will print this line below the table, and then we will print, therefore after the iteration, number of iteration, the root x2 is equal to the last value of x2, and that get ch open and close parenthesis will hold the terminal until we press any key. Now let's try to run the program, build and run this program. Okay, let's go to the terminal, and this program obtains a root of third to 10th degree polynomials. So the user is prompted to enter the degree. Let's use the polynomial being used in the first program. We will enter the degree of the function as 3, and then the coefficient of x cubed is 1. The coefficient of x squared is equal to -4. The coefficient of x is 1, and the value of a sub 0 is -10. We will enter also the precision at 6, the accuracy at 0.001, and then x sub 0 is equal to 0 and x sub 1 is equal to 1. So after 13 iteration, the root x2 is 4.306913, which is equal to the result of the first program. We have the first program for x cubed minus 4x plus x minus 10. We have the result of 4.306913 and the tabulated result table. Okay, for the second program, we have also program for third to the 10th degree polynomials. Comparing the first and second program, they have the same tabulated results, only that the first program requires only 4 parameters, namely the x sub 0, x sub 1, the precision, and the accuracy. Though the first program can solve transcendental and polynomial equations, it can only solve the embedded equation in the program, in this case x cubed minus 4x plus x minus 10. While the second program can solve third to 10th degree polynomials, it requires all the parameters, including the degree of the function, coefficients, the precision, and the accuracy. The approximated root is the same for both programs. For the third degree polynomial x cubed minus 4x plus x minus 10, which is equal to 4.306913, okay, the same. Okay, our references are Wikipedia, mechtutor.com, Fizwiz, bragitoff.com, c++.com. Okay, this concludes my C++ program. I hope this presentation is comprehensive enough to understand how to create a program in approximating a root of a given function using the second method technique. Thank you very much for watching.